Another area where gravimetric analysis is frequently used to establish analyte concentration is establishing the weight percent of an analyte in an impure solid. So this is often used in quality control or the analysis of anthropogenic human-made materials, specifically deliberately engineered materials such as plastics, semiconductor components, and a variety of materials. In terms of establishing the concentration of the analyte, nothing has changed about how we're going to use the stoichiometry of the gravimetric analysis precipitation reaction and the chemical formula of the product to establish the concentration of the analyte. Often these problems can seem a little more intimidating though because they're more wordy, they refer to more steps, and they may make reference to more obscure chemicals. But the central principle doesn't change. So for instance, here's a worked example from section 27.1 of Harris where we look at an impure solid containing the organic molecule piperazine. We're going to digest the original sample and treat it with acetic acid to precipitate the piperazine out as piperazine diacetate. This precipitate was collected and dried and found out a final mass of 0.7121 grams. This obviously is a more complicated setup to a gravimetric analysis problem, but the central principle hasn't changed. We're asked to find the weight percent of piperazine in the original sample, and we're given a balanced chemical equation to show the reaction stoichiometry of the precipitation reaction. Now, for those of you who haven't had organic chemistry yet, this can again seem a little bit more intimidating because they're using an abbreviated Lewis structure in their chemical reaction scheme. See these solid bond lines here, which is more common to organic chemistry. And if you haven't had organic chemistry yet, you may find this notation confusing, which is okay. Don't let that be a barrier. This is something that Harris will use on occasion, but it won't come up a lot. Understanding the full Lewis structure is not really central to solving the problem here because we're just going to make use of chemical formulas and molecular weights. As a heads up, when you see these kind of bond line connections, what it is essentially indicating is that there is a 2-carbon chain connecting these two nitrogens. So you have nitrogen, carbon, carbon, nitrogen, and in this type of Lewis structure scheme that's more common to organic chemistry, the carbon atoms are just omitted and replaced with these solid lines. So if you're not familiar with that notation, don't let that throw you. It's not crucial to the problem-solving process. What is key is that the reaction stoichiometry here is 1 molecule of piperazine is going to react with 2 molecules of acetic acid to produce the precipitate piperazine diacetate. And what is also central to the problem is Harris has given us the molecular weights of the product and both of the reactants. So for instance, formula mass, same equivalent terminology to molecular weight of piperazine, 86.138 grams per mole. Acetic acid is 60.052 grams per mole. And the product, piperazine diacetate, has a molar mass of 206.424 grams per mole. So this is really the information we need to do gravimetric analysis, is we need to know the stoichiometry of the reaction and we need to know the molar masses. And we don't actually need to pay too much attention to the chemical structure of our analyte right now, as long as we know the molar mass. All right, so in terms of solving this problem, in principle, the same as any other gravimetric analysis reaction, the idea is we're going to take the final mass of the precipitate to figure out how many moles of the analyte were in the original sample. Then we're going to use the molar mass of the analyte to calculate the number of grams of the analyte present in the original sample. And then to find the weight percent, we are just going to take that grams of analyte, divide it by the total number of grams, and multiply by 100% to get the weight percent composition of piperazine in the original sample. So there's more steps here. It's a little more complicated, but we're just lining up skills that you already possess to answer a slightly more complicated gravimetric analysis question. All right, so the first step will be the same as ever. We know the mass of the final precipitate, 0.7121 grams. This is the chemical formula of the final precipitate over here. More importantly, we know that its molar mass is 206.242 grams per mole. Every mole of the precipitate contains 1 mole of the piperazine because 1 mole of piperazine complexes with 2 moles of the acetic acid to make 1 mole of this product. Therefore, we can say we want to find the moles of piperazine in the precipitate. We'll take the 0.7121 grams of the precipitate. I often abbreviate precipitate just PPT, so kind of add that to your lexicon. I'll use that a lot. Instead of using the chemical formula, I'm just saying the precipitate because the chemical formula is pretty long. It's easier to just write precipitate. 1 mole of the precipitate has a mass of 206.242 grams, and 1 mole of the precipitate contains 1 mole of piperazine, our analyte. By taking the 0.7121 grams of the precipitate and dividing by the molar mass, and remembering the reaction stoichiometry locks up 1 mole of the analyte to form 1 mole of the precipitate, we see that our 0.7121 grams of the precipitate should contain 0.00345,274 moles of our analyte piperazine. So what we're going to do with that then is now we want to take the molar mass of piperazine and use that to convert and figure out how many grams of piperazine we had in the original sample. So the mass of piperazine that ended up in the precipitate, 0.00345,274 moles of piperazine, times 86.138 grams of piperazine per mole, means that there were 0.2974 grams of piperazine in the original sample. Now, notice we already know the sample wasn't pure piperazine. It had a mass of 0.3126 grams, and only 0.2974 grams of that original sample mass were actually piperazine. So to find the weight percent of piperazine in the original sample, our last step will be to take the mass of the piperazine, divide it by the original sample mass, multiply by 100%. So that is 0.2974 grams divided by 0.3126 grams times 100%. The original sample was 95.14% piperazine. And we're entitled to 4 sig figs in our answer because we had 4 sig figs in both the original mass of the sample and the final mass of the precipitate. So notice here you can also use gravimetric analysis to establish the concentration of an analyte in a solid mixture as well as a liquid solution. The principles don't change. In this problem, we're just lining up more skills like the definition of a weight percent and looking at a slightly more complicated precipitation reaction to establish the concentration of the analyte in the original sample.